Welcome back to our next video in 9.8 on power series. We're continuing in our discussion on this idea of infinite polynomials, or as we call them, power series, and really trying to answer the question as we presented in the last video of what is the domain of these power series. For what values of x does the series converge? What am I allowed to plug into this function? And we talked about how we're going to construct this, how we're going to find this, and the main key is to use a test, a series test, and use the ratio or root test. And we're going to work that out, and we're going to see how that is going to give us the interval and radius of convergence and find the domains of these functions. Now in this case, because of the factorial in this power series, I'm limited to the ratio test. And so we're going to use the ratio test to determine for what values of x this series converges. So remember how the ratio test works. You take the limit as n goes to infinity. The absolute value, and this is what's important, this is what's going to give me my two-sided inequality that we talked about in the last video. We have the n plus 1th term over the nth term. And we take its value and we see what happens. Now, we could simplify this expression. If I multiply by the reciprocal, this is going to end up giving me n factorial over n plus 1 factorial. This is going to end up giving me x to the n plus 1 over x to the n. If you multiply by the reciprocal, remember this is in the numerator, right? So if you multiply by the reciprocal, this goes in the numerator and this goes in the denominator. So we see it here. And I wrote them next to each other so that we can see what cancels. And so we end up getting the limit as n goes to infinity, absolute value. Remember, these factorials reduce now to 1 over n plus 1. The 1 through n of this factorial cancels with the 1 through n of the bottom one, but the bottom factorial has that extra last term. Here we reduce powers, just think exponents. This just simplifies to now x. And notice, remember that n is positive, and so we don't need the absolute value around n. We can just write it as 1 over n plus 1. We do need the absolute values, and this is important, around x. And that's because we do not know what x is. X is an unknown variable. It could be negative, it could be positive. So we just need to know what it is, right? Or we don't know what it is, so we're leaving the absolute value with it. We also notice that, or remember that this is very important as well, the limit has to do with n, not x. It has nothing to do with x. X is just some arbitrary unknown. And so when I take this limit, it does not affect this term. This is not infinity over infinity or an indeterminate form. In fact, just to not confuse us, we can go ahead and pull that absolute value of x out. And write it like this. Remember, the limit is with n. The only thing contained in n is right there. Now, when we take this limit, we see we get 0. 1 over infinity, that's not indeterminate, that goes to 0, so we get the absolute value of x times 0. Now we see something interesting happening. If we go back up to this original power series, let's first ask ourselves, okay, well, where is this power series centered, or its center of convergence? What value of x can I plug in that will make this converge? And really, you just need to think of what will make your variable 0. What will make that polynomial piece 0, right? Because we want all the polynomial terms to disappear and only be left with your constant. What will do that for us is replacing x with 0. That will make all the polynomial terms disappear and then only leave me with the constant term. And so we can write over here, we can write that this power series is centered at 0. And how far can we move away from the center? Well, we use the ratio test, we get this. And remember how the ratio test works. Right? It's not that we just get an answer. We take our answer and we do something. Remember, the ratio test says, okay, you take this limit. If your answer is less than 1, then the series converges. Remember, that's the condition for the ratio test, and same for the root test. If this number is bigger than 1, the series diverges. And unfortunately, if it equals 1, we don't know, which is actually going to lead us to another question. And so in this case, we have our answer. We get the absolute value of x times 0. And really what we want to be concerned with now is for what values of x is the absolute value of x times 0 less than 1? Now, this is a trivial question because, well, you'd say any value of x. Why? Because it's times 0. So any value of x would work. So as long as the value of x is less than infinity, this works. So it's some number. Any number will do. And so what does that tell me? That tells me in this case that the radius of convergence is infinity. How far can I move away from my center and still converge? For what values of x is this statement less than 1? Any value of x. How do I get infinity here? If you just divide both sides by 0, which you never should do, that's technically not allowed. If you divide both sides by 0, this would tell me the absolute value of x needs to be less than, well, dividing by 0 would make this side blow up. 1 over 0, vertical asymptote, or infinity. And so we need this to be true. So how far can I move away from 0? What's the absolute value of x, where absolute value is two-sided? How far can I move away from 0? The distance away from 0 is infinite. And so r is infinity. And so what is the interval of convergence, which I'll abbreviate as IOC, would be negative infinity to infinity, or all real numbers. Now, where this becomes interesting is, you remember that this was the Taylor polynomial, or the Taylor series for e to the x. And I have just shown you now that the domain of this polynomial is all real numbers. The domain of e to the x is all real numbers. And so that tells me that this is the same as e to the x for all real numbers, that e to the x is equal to this polynomial everywhere. And so we actually get the final statement now, and we typically won't have this, but this was a special case to start with, because we know that this was a Taylor series for e to the x, is that e to the x, now I can say with confidence, is actually equal to this. Why does that become useful? Well, remember, the whole thing about series is we didn't really know the sum of a series in general. But now I can take this bit of information and I can tell you that the sum of this series is e squared. That this series converges, and what is its sum? E squared. Why? Because this series is equal to e to the x. So if I replace x with 2, I would get 2 to the n over n factorial here, this infinite sum. And I know that this is equal to e to the x, so this would be equal to e squared. So what is the sum of this series? E squared. If it was 3 to the n over n factorial, it would sum to e cubed. 5 to the n over n factorial, e to the 5th. And so we can take this and actually use power series to find sums of series that we previously could not. Assuming we know that it comes from a certain function, right? If we can write our power series as a certain function, like in this case, e to the x. In general, that's not going to be true, or we won't be able to do that, but it's an interesting case to start with. And so this is the one extreme case where the domain is all real numbers, right? We get some sort of weird thing going on here, and we see that, okay, well, now that really means that x can be anything, and so the radius is all real numbers. And this is a possible situation. Let's look at another one. In this case, we have negative 1 to the n over n times x minus 1 to the n. And let's find the radius and interval of convergence here. Now in this case, because of the construction of my power series, I'm going to use the root test. So we're going to find the radius and interval of convergence. And I will do so by using, in this case, the root test, because I have nth powers. And I know from a previous video that the nth root of the n, if I take that limit, it goes to 1. So the root test says take the limit as n goes to infinity, the nth root of the absolute value, my series. Remember that we're taking it in terms of n, so x is just an arbitrary variable right now. The absolute value gets rid of the negative 1 and just makes it 1, so now everything's positive, so that negative 1 to the n disappears. The absolute value of n is just n, because n is positive, starts at 1. We do need the absolute values around x minus 1, since again, we do not know what x is. X is an arbitrary variable. So I just moved the absolute value through, took the absolute values I need to take. The negative 1 to the end disappears because we made everything positive. The absolute value of n does nothing since n is positive anyway, and we need it here. Now, root split up over numerators and denominators, so we can rewrite it. The nth root of x minus 1 to the n reduces to just the absolute value of x minus 1, and we get the nth root of n in the denominator. Now again, remember that the limit is about n, not about x. And so to avoid confusion, x can be pulled out of this limit. That x term. Now again, we took the limit of the nth root of n in a previous video and realized that that is 1. And so we end up getting x minus 1 times 1. The absolute value of x minus 1 times 1. That times 1 looks funny with all these slashes. So x minus 1 times 1, and times 1 does nothing. So we're just going to get this. And we have the same question. Now that we have our answer, for what values of x then is the absolute value of x minus 1 times 1 less than 1? Why less than 1 again? Because that's the ratio test and the root test. Both have the same conditions. We want to know, when is this limit that I just took less than 1? Because if it's less than 1, it converges. If it's greater than 1, it diverges. If it equals 1, we don't know. Now this statement, right, like we said, is a two-sided inequality. It says that, well, then x minus 1 needs to be less than 1 or greater than negative 1. So what does that tell me about x? It needs to be less than 2 or greater than 0. Really, we can think of it as a distance away from the center. If you look up here at the beginning, remember that this is a power series centered at 1. We know that this series converges if you let x be 1. Why? Because that will make all the polynomial terms 0 and then leave me with just the constant term. And so the center of my series is 1. We wanted to know how far we could move away from the center, move away from 1, and still converge. In this last example, we saw that it was infinite. In this example, it's finite. The distance you can move away from 1, which is represented by this statement here, needs to be less than 1. And so I can move 1 unit this way and 1 unit this way. What does that now give me? It gives me 2 as an upper limit and 0 as a lower limit, right? 1 unit up to 2, 1 unit back to 0, giving me this. And so really, if we understand this statement as a whole, we can jump straight from this to our interval 0 to 2. But if not, we can go the route around it by writing it as a two-sided inequality and getting an interval. 0 to 2. Again, that's not a point, it's an interval. Now comes the question of whether or not they should be brackets or parentheses. Here we didn't have to worry about it because, of course, at infinity you can never have a bracket because you could never be infinity. Infinity is just a concept. So we never had to worry about bracket or parenthesis in that example. In this one we do. Because of how the ratio and root tests work. They say if you're less than 1, you converge, and if you're bigger than 1, you diverge. Meaning, in this case, if I'm inside this interval, if I'm 1 unit away from 1, I converge. If I'm more than 1 unit away from 1, I diverge. So if I'm outside this interval, I diverge. But what about if I equal 1? What if I am 1 unit away from the center? What if I am the 0.2 or the 0.0? Do I converge or diverge? And unfortunately, the root test or ratio test will not answer that. So we are inconclusive at x equals 0 and 2. So how do we know? Well, we have to check it by hand. What that means is I need to plug 0 into the function and see what happens. I need to plug 2 into the function and see what happens. And then I need to use everything I know about series to determine whether or not it would converge or diverge. If I replace x with 0, let me give myself a little more space here. If I replace x with 0, we get a sum, -1 to the n over n. Replacing with 0 gives me another -1 to the n. But wait a minute. if n is 1, they're both matching in exponents, right? So if n is 1, we get -1 times -1. If n is 2, it's +1 times +1. If n is 3, it's -1 times -1. But wait a minute, a negative times negative is always positive. And so actually, regardless of what n is, this series reduces to just 1 over n. Because of the double negative here. Just makes 1 now. It's no longer alternating, right? It's just 1. Wait a minute, I know from series that this diverges. This is a divergent p series. P is 1. And so what does that mean? That means at 0, we better leave it as a parenthesis. So I erase it to just not change it. What about at 2? I'll write this one in green to give you a hint as to what's going to happen. If I replace n with 2, or x with 2, I get 1 to the n, which means absolutely nothing. It can just go away, because 1 to the n is 1. And they don't cancel. I'm left with this alternating series. And by the alternating series test, this series actually converges. And so what does that mean? That means at 2, it is within the domain of this function. 2 is an okay value itself. And so at 2, I should not leave it as a parenthesis, but write it as a bracket. And so my interval of convergence is 0 to 2 with a parenthesis at 0 and a bracket at 2. My radius of convergence is 1, right? It's 1 unit away from the center. All right, so the radius of convergence is found from this statement, 1 unit away from the center. My interval is also found from here, 0 to 2. And then we need to check the endpoints. It's very important to check those endpoints because of the inconclusiveness of the ratio and root test. And so this is a nice example of the in-between of, okay, it's not infinite radius of convergence, it's finite, and then I need to check the endpoints. And so let's do another one as well and get a little more practice in these types of series, power series. And so if we come over here to this power series, first we'll notice, of course, where it's centered. In this case, -2, right? Because that's the value of x that will make the polynomial term disappear when x is -2, leaving me with just a constant. And so we know it will converge if x is -2, so we're centered at -2. Now the question is, how far can we move away from -2? Again, in this case, because of how this power series looks, I'm going to use the root test. Root test is a nice test to use. And so the root test tells me to take the limit as n goes to infinity, the nth root of the absolute value of all of this. Because n starts at 1, the absolute value does nothing to the 2 to the n, 3 to the n, or n, so we can just move through it. The absolute value does need to stay on the x plus 2 because, again, we don't know what x is. Root split up over multiplication and division, so we can distribute this root over every term here. The nth root of 2 to the n is just 2. The nth root of n, well, we'll have to take that limit. The nth root of 3 to the n reduces to just the number 3. And x plus 2 to the n reduces to the absolute value of x plus 2. And again, just remember, the limit has to do with n, not with x. So everything that does not have an n in it can be moved out, and even that 2/3. So 2/3 x plus 2 in the absolute value can be moved. We do need to take the limit, though, of what remains, which is 1 over the nth root of n. But like we learned in a previous video, the nth root of n goes to 1, and then goes to infinity, leaving me with 2/3 times the absolute value of x plus 2. And so that's the limit I get in terms of x. And now we have to answer the question, for what values of x? Is 2/3 times x plus 2 less than 1? Again, why? Because of the ratio and root test. They tell me I want to know when this limit is less than 1. That is where I will converge. Now, because of the 2/3 on this side, I'll isolate the absolute value term to give me 3/2, 1.5. And what this tells me now is it tells me how far I can move away from -2. I can move 3/2 units. If we want to think about it one way, right, we can write it like this as a two-sided inequality, and we need to subtract 2 from everything. So I can move 2 units away from I can move 1.5 units away from -2, and so x can be between, well, if I subtract 2 here, I get -1/2. And if I subtract 2 here, right, just think of 2 as 4/2, so -4/2 gives me -7/2. So -3.5. So what is my interval? Well, my radius is 3/2. That's how far away I can move from the center, giving me my interval of -7/2 to -1/2. There's my interval. Now, again, the question, just like in the last example, is whether or not these should be parentheses or brackets. And that we do not know because of the inconclusiveness of the ratio and root test. They say, okay, well, I do know if I'm less than 1, so if I'm in this interval, I converge. And if I'm bigger than 1 or outside this interval, I diverge. And if I equal 1 or if I'm on the endpoints of these intervals, I don't know. So the endpoints we need to check by hand. And so there's no easy way about it but plugging in -1/2 and -7/2. So if I plug in -1/2 for x, remember, -1/2 plus 2 is 3/2. So we get f of -1/2, if I plug it in, n equals 1 to infinity, we get -1/2 plus 2, which is 3/2. And we get this, right? 3/2. Splitting the n power over the 3 and the 2, and the 3/2 gives me this. And why do I do that? Because, well, then these cancel. And we're actually left with a p-series, 1 over n. This p-series diverges. P is 1. And so what does that mean? That means at -1/2, it better stay a parenthesis. Okay. Well, what about -7/2? Well, -7/2 plus 2 is now -3/2 instead of +3/2. And so actually in this case now, what we're going to end up getting is 2 to the n over n times 3 to the n. -3/2, we can split up the n power over the negative, the 3, and the 2. So I split it up over the -3/2, so over the -1, the 3, and the 2. And again, the 3 and the 2 cancel, but now we're left with an alternating series. And even though I wrote it in red, this series converges by the alternating series test. I agree it conditionally converges, but it converges as an alternating series. And so that actually means at -7/2, I better change this to now a bracket. And so again, another more interesting case, we have some sort of finite interval, and one of the endpoints works, the other one doesn't, and this is now the domain, or the interval convergence. Again, what that means is, for any x value within this range, this power series will converge. So specifically, for example, -1 is in this range, meaning if I replace x with -1, I would have a convergent series. If I replace x with 1, though, or even 0, right, we'll use 0 as an example. If I replace x with 0, 0 is outside of this interval. And that tells me now that if I replace x with 0, this is a divergent series. And so we're answering something about the convergence of a series, given certain values of x. And so let's just do one more to really drive it home. In this case, because of the construction of this power series, I'm forced to use the ratio test. And so, ratio test here. The limit as n goes to infinity, absolute value All right, n plus 1th term. Over nth term. Where is this power series centered again? -1, so let's just write that down. That's the value of x that makes my polynomial term 0. That's what will make it converge for sure. And now let's figure out how far we can move away from -1. If we just are comfortable with working with fractions instead of having to multiply by the reciprocal, the 2 to the n reduces with the 2 to the n here, leaving me with just a 2. Now when I reduce it, the n factorial reduces here to just leave me with n plus 1 in the numerator. The absolute values get rid of these pieces, so actually they just disappear. We can just ignore them. And the x plus 1 to the n, x plus 1 to the n plus 1, again, powers reduce. In this case, just leaving me with a single x plus 1 in the numerator. And so you notice everything down here is gone. The only thing that remains now is the limit as n goes to infinity. The absolute value does nothing for the n plus 1 or the 2. I do need the absolute value around the x plus 1. And we're left with this. And so what do we get? Well, we get the absolute value of x plus 1 can be pulled out times the limit as n goes to infinity of n plus 1 over 2. And in this case, this limit blows up. And so what's my answer? It's x plus 1, absolute value, times infinity. And so we have the same question. For what values of x? X is the absolute value of x plus 1 times infinity less than 1. Well, no value of x because, well, that's infinity here. No value of x except possibly when x is -1. When x is -1, that we get 0 times infinity, which is actually an indeterminate form. We're not sure. But any other value would definitely not work. So the only value of x that would work would be possibly -1. Does it work? Well, that would be the constant term of this polynomial. And so we actually do get an answer, right? When n is 0, we get 1 times 1 times 1. So we get 1 here. That's my constant in front. X plus 1 to the, or sorry, -1 plus 1 is 0. So we don't get the constant term here, right? It's gone. And so we just get 1 when x is -1. We'll just get the constant term, which is 1. And so we actually do get something finite when x is -1. Outside of that, nothing. If we want to think about it in terms of radius of convergence, if I divide both sides by infinity to isolate my absolute value term, we get 0. 1 over infinity. Just like here, in the last example, it blew up to infinity. And so we don't need to think about that, but what this means in this case is r is 0. How far can I move away from the center? Nothing. And so what is the interval of convergence? IOC would just be the single value, -1, the center of this power series. This is the other extreme case. So this series never converges except for at center at -1. And so I hope this was useful, got us some good practice in fleshing out how do we find intervals of convergence for power series. And so in the next video, we move on to 9.9, which again, we're continuing with power series, but we're going to use another tool to write functions as power series. And that's where we're going in the next section, which is 9.9.